Hello, it's Nathan, I'm in the stream setup today because I wanted to document a talk that I gave in the dynamic seminar at my school about, and the title's on the screen already, extremal F-exponents of finitely irreducible conformal graph-directed Markov systems. So this will be more of like an academic talk documentation video. So I'm going to go through this talk that I gave. Um, the goal of this talk is to was to give other people at my institution a view of the apparatus that I work with when I do the multifractal analysis that I do without going into all of the nitty-gritty details of doing that multifractal analysis and developing some of the tools necessary to complete the multifractal analysis that I do in the first part of my thesis. Well, it might be my whole thesis. It depends on how productive I am over the next year, but it's got a lot of stuff in there. It exists on the archive already. So this paper, multifractal analysis of F-exponents for finitely irreducible conformal graph-directed Markov systems, is the basis for this talk. It's by me. And it's work that I did under the advisement of my PhD advisor, Dr. Mariusz Urbański. So this talk will go over, without doing any of the details or any of the proofs, it will introduce to the viewer the first, well, not the first section of the document, but sections 2 and 3 of this paper, of which there are 5. So with that being said, I should give some setup for what we're doing. Also, it's all written down. It's all on paper, so I will be sort of going between things to make sure that I write what I want to write down. So let's do the thing. All right. So to begin, the setup here is there are a lot of mathematical objects that I'm not necessarily going to define for you, but hopefully I give you an idea of the flavor of this type of thing. So let me switch this to a different color. So setup as well. First, I need there to be a conformal graph-directed Markov system, which we sometimes abbreviate as a CGDMS. And I need a Hölder family of functions. So all of these functions are Hölder continuous on cylinders, and well, they're Hölder continuous, and they go from the metric space, because they're not yet on the symbol space, so they're not necessarily on cylinders, but they go from the associated metric space to the real numbers. Yeah, and these are going to be a strictly positive. Hölder family of functions, which we usually call potentials in my area. And then lastly, we're going to just say that J is the limit set of the conformal graph-directed Markov system. And there's this little aside that I want to do, because I'll come back to this sort of diagram throughout the talk, or at least a few times during the talk. So just put down a line. There we go. So there's this sort of, I'm going to draw it as a diagram. It's not necessarily a diagram in the algebraic sense. Some of the stuff commutes, not all of it does. And it might help you sort of like orient yourself in what I'm doing. So when you're doing this dynamics thing with conformal graph-directed Markov systems, usually where you start is you have some limit set, which we'll call J, that is associated to a dynamical map T. So you're able to iterate T over and over and over again. And by taking inverse branches of t, you end up with this conformal graph-directed Markov system. That better. Phi, which has a symbolic representation, which is some list of symbols. And so if you're not familiar with symbolic representations, the things you should think about are number-based expansions. So things like things like decimal expansions, binary, ternary, all of those whole number base expansions. All of these are examples of a symbolic representation of a conformal graph-directed Markov system. So I'll denote that as EA infinity. And in symbolic dynamics, you have a shift map. And how the symbolic representation relates to the limit set is that you can project a symbolic representation down onto the limit set in order to realize a point in the limit set. So this is the shift map. It's going to take a sequence of symbols and just kill off the first coordinate. Okay, great. Next, I want to tell you about how what an F-exponent is. So in this diagram, what happens with F-exponents is that you have these family of potentials, and they work on different points in J. And you can take these time averages of these potentials. So I want to know like some valuation of long-term behavior of this dynamical system. And so what I do is I go ahead and I take a time average or a Birkhoff average of the system, which I'm going to write this way. This is not 100% correct because I want to suppress some of the notation here just because it can get complicated really fast. So you take some time average, and this Sn is some way you're summing over the functions in F. And this is going to give you a real number because all of those functions in F are real valued. And so this limit could be infinite, or it could just not exist. I'm distinguishing between the two because we sometimes distinguish between the two in the multifractal analysis. And then if I want to do this symbolically, what I'll do is I'll go ahead and what's this process called amalgamation. So yes, amalgamation. I always say amalgamation for some reason, but it is amalgamation. And that gives you a way of doing an evaluation on the symbolic space. And this one I'll actually write out. So this one is the limit as n goes to infinity of 1 over n times the sum from j is equal to 0 to n minus 1 of what's called the amalgamated function, f tilde, of the jth shift of whatever symbolic point that you're taking. And so that is the Birkhoff average with respect to the amalgamated function of the family F. And you can sort of go back and forth between these two things under certain circumstances. And the way that you move backward is you do this restriction to the cover by one symbol cylinders of your space, which is not important for this talk, but I'm just wanted to put it out there that there's like some notion of like you can go between these two things. Again, this is not an algebraic diagram, but it's just supposed to orient you into how I'm moving about the spaces. Again, I haven't defined a lot of things yet. I'm about to do that. But this is the overall picture. And we'll come back to this in a second here. So let me border this off because I will need it later. I don't want it to be that high because I have questions that I will pose here in a second. So back to the setup. So we had that diagram, and we want to go ahead and I want to tell you things. So I need to tell you what the main object of this talk is. I need to tell you what an F-exponent is. So we're gonna work symbolically. So first, I want to amalgamate these potentials. So here's a definition. So the amalgamated of a family of potentials or functions is given by, and this will be F tilde, is by definition equal to, oh, I should say what we're evaluating at. So F tilde of omega is by definition equal to the first symbol in omega's corresponding function in the family evaluated at the realization of the shift of that symbolic, the original symbolic representation that you plugged in. And this is for every omega within your symbol space. So it translates information about functions on these metric spaces to a function, singular function, on your symbolic dynamical space. And so once you have that amalgamated function, we can also define what the F-exponents are. So for omega within EA infinity, which is a symbol, so for some symbolic point, the F-exponent at omega is given by C of omega, which is by definition equal to that limit that I put over in the diagram over here. So this will be equal to the limit, then goes to infinity, 1 over n, sum j equals 0 to n minus 1 of F tilde evaluated at sigma j of omega. All right. And the idea here is that I want to somehow minimize this thing. So I should tell you about what the standard behavior of these exponents are. And we do this by looking at certain measures. And again, I'm being very general at the outset with these definitions, but I'm going to do some examples here in just a second. So let's see. So further, for mu, a shift invariant Borel probability measure, the characteristic F-exponent for mu is given by, and we'll write, I want to make sure I do this right for notation going forward. Yeah, is given by the integral over the symbol space of the amalgamated function with respect to that measure. And in the case that mu is an ergodic measure, that integral, and this will be by Birkhoff's ergodic theorem, will almost everywhere be equal to the F-exponent at a single point for mu almost every omega within EA. Right? So I can figure out what happens most of the time with respect to some measure very quickly. And that's something to note here. I should update this diagram. I should say that this limit here by Birkhoff's ergodic theorem, right? This is equal to an integral over the symbol space of the amalgamated function for almost every omega within EA infinity. Okay, so we have some idea of how we can move around, and I can figure out what the characteristic thing is quickly. So just for example, sometimes in number theory, people care about the average of digits in the representation of different numbers within different number systems. And so for the Gauss map, so here's an example. Let me draw a line really quick. So here's an example. That example. So we go ahead and let f be equal to log e, where e is a element of the alphabet and not Euler's number in this case, and my log is natural, so this is the natural log, which is common in my area to just use log instead of natural log, and then e for a symbol in the alphabet. So if you have your family just be log of whatever symbol, then this defines the kitchen exponent, or the Kindchen. All right, so by kitchen exponent, I mean that you do this sum process for a particular point, and you can figure out what the kitchen exponent is for a certain symbolic representation of a point, and it will just end up averaging the digits in some sense, or it'll give you an idea of the average of the digits in some sense. In this case, it'll be like more of a geometric average of the digits, if I remember this correctly. So, yes. So that just is what that family always defines the kitchen exponent for a particular system. And if we let t from 0, 1 to 0, 1 be the Gauss map, which is the continued fraction map, which is t of x is equal to 1 over x minus the floor of 1 over x. So you're just looking at the reciprocal of a number, and you're killing off the whole part. This ends up being the map that generates your continued fractions. We have a conformal graph-directed Markov system, phi, which is equal to 1 over x plus n, which goes from the interval from 1 over n plus 1 to 1 over n to 0, 1. And it looks something like this, where if you're at a half, you're at a third, and then you're at halfway between there, a fourth, and so forth, because I can't draw all of these, but it sort of looks like this. It goes down for quite a while. Um, Here, the characteristic kitchen exponent with respect to the invariant measure of the system is going to be 2.6854. In particular, so with respect to the Gauss measure, which is the invariant measure for the Gauss map, it's absolutely continuous with respect to Lebesgue measure with bounded Radon-Nikodym derivative. So we can also say that this is true for almost every point in the unit interval in the traditional Lebesgue sense of almost everywhere. Almost every point in 0, 1 has exponent or kitchen exponent given by the integral of f tilde d mu g composed with pi inverse of EA infinity. And I don't want to, for time's sake, just tell you about this mu of g pi composed with pi inverse measure because I don't have enough time to explain it. And I'm already running kind of long. Oh no, actually I'm doing okay. It's only been 20 minutes. That's what I wanted to do in 20 minutes. So I don't want to go through what that preimage means and why we can do that in this particular case here, because that's not the point of the talk. The point is to talk about these exponents. Right, so I can find a characteristic one, and we can do this for a lot of different number systems. So this is for continued fractions, right? So let me just say that this is continued, or at least a dynamical representation of continued fractions. Right. But we can also do this for other number systems. So here is let me just make sure, yeah, we're doing good on moving down the page. So I also want to talk about a different numbering system that's been sort of constructed as a baby example for this talk, and that's of Lou-Roth expansions. So a Lou-Roth expansion is defined by some descending sequence of terms in the unit interval. Let me make that straight. Okay. So I'll graph this in a second over here. But let's let S from 0, 1 to 0, 1 be the Lou-Roth expansion. Defined by the descending or strictly decreasing sequence of terms in the unit interval, 1 over 2 to the n. I think that's what I want. Yeah, so in particular, I don't need to define the sequence for this. I instead just want to say that it has inverse branches. Bn inverse, which goes from 1 over 2 to the n to 1 over 2 to the n minus 1 to 0, 1 onto, and these are lines. So each of the form y equals mx plus b. So in particular, if we take this map with these inverse branches, we get a conformal graph-directed Markov system. Where phi n goes from 0, 1 to 1 over 2 to the n to 1 over 2 to the n minus 1. And these maps are all still lines, and there are infinitely many of them. And so what S looks like, is that you just So you're at 1 to 1/2, and you draw a line up to 1. If I can do this precisely in this program. So let's do that there, and then this would be at 1, and then we find a fourth. Oh, that's right. I need to. There we go. Okay. And we do the same thing, and then we do an eighth, and we do the same thing, and we just do that forever. We make all of those lines. This defines this gives you a Luroth expansion. It's just another number system, and we can look at what's called its Lyapunov exponent, which is the exponent that corresponds to the Hausdorff dimension of the limit set. So in particular, I want to just focus on points that have unique codings, which I can do because the system satisfies the strong open set condition. So J1 is equal to x within 0, 1, such that there exists a unique omega within the symbolic representation, such that the realization of that unique thing is x. Then I can go ahead and calculate the Lyapunov exponent. So first we note that Lebesgue measure is ergodic for this system. And the Lebesgue measure of this set of unique coding points is going to be 1 because we satisfy the strong open set condition, and our conformal graph-directed Markov system is finitely irreducible. In fact, it is a conformal iterated function system because there are no restrictions between symbols. And the positive Lyapunov family minus log phi, which is equal to this collection of potentials log of the first of the absolute value of the first derivative of the eth function in the conformal graph-directed Markov system has amalgamated function, which just by definition will be, and we have special notation for this one. So I'll use capital C of phi of omega, and I want it to be the positive Lyapunov family, so I'll make a negative there. It'll be minus log absolute value phi omega 1 prime of pi of sigma of omega. And that's just the definition of amalgamation. And in this case, for these particular maps, you'll actually get the first symbol times log of 2. So whatever number the first symbol is as a number times log of 2. And that should sort of make sense. The intervals on which these full lines exist is 1 over 2 to the n, so you're getting smaller and smaller and smaller, and your derivatives are getting exponentially small as you go, because it's not these lines that I'm looking at. It's not these that correspond to S, but I'm looking at the lines that correspond to phi. So with that, almost every x within J1 has Lyapunov exponent minus integral over J1 of C phi composed with pi inverse of x d Lebesgue, which will be, it turns out that this will be a discrete sum of minus n log 2 over 2 to the nth power, which is equal to 2 log 2. So I can calculate these characteristic exponents, but there's something that is going on here in the background, right? There's more detail that we're not picking up because we're only doing this for almost every point in the unit interval with respect to some measure, right? So almost every point within the unit interval with respect to some measure. In both cases of these examples, they're absolutely continuous with respect to Lebesgue measure, but there are more measures on the unit interval, and I want to figure out what the extremal F-exponents are. So I need to do something in order to figure out how to detect and describe what is our worst case scenario or best case scenario. But in this case, or in this talk, there will only be a worst case scenario because I'm only thinking about infinite alphabet systems. And so the thing to note here is that whenever we have these ergodic measures, so in this case where we have Lebesgue measure that's ergodic, right? So here when we have Lebesgue measure that's ergodic, and in this other previous case, when we have the Gauss measure, which is the ergodic invariant measure for the system, we only pick up one exponent, right? So in the case of the Lyapunov exponent of this Liouvre expansion, it was 2 log 2. In the Kitchen exponent of the Gauss map, it was about 2.6854, and there's a better approximation of that number somewhere out there I guess in Fon et al. Is the paper that I reference, or that my work is a generalization of. And so in this apparatus here, the thing to note, right, is that, or the remark here, so let me do this, I guess, in green. So the remark, or I guess that won't look great. So remark, if mu is ergodic, it only detects one F-exponent. And so this translates this problem of finding these F-exponents to and finding these extremal F-exponents into potentially an ergodic optimization problem. And it does turn out that this idea works, and that if you think about the measures, you can end up minimizing these things, and that's the point of this talk, right? So there's this 3-step plan of how we approach this. So the question is, what is the minimal F-exponent achievable and well, the idea here, do a different color, is, well, one, we need a family of ergodic measures that detect just one F-exponent. So we need a family, defined family of ergodic measures that detect one exponent. 2, I want to somehow justify performing a limit of of certain subsets of that family. And this is going to be in the space of measures. And then 3, I want to go ahead and connect that limit to a quantity that I can do numerics on. So connect, because integrating with respect to some random measure that you construct in this in maybe not a so tractable way is hard, but we can connect these measures to quantities that we can do numerics on. So we could connect the limit to a quantity that we can do numerics on. So connect this limit to a quantity that we can calculate. All right. That's the game plan. But in order to pursue this, I have to tell you just a few facts, and I won't prove really anything, but I'll tell you sort of like what the toolkit is. So this plan does work out. You can find the family measures, you can perform a limit on these family measures, and you can connect that limit to a quantity that is where you can do some numerics on, or you can calculate it exactly in some cases. And so the first thing I need to tell you, though, is about the variational principle. So where do these family of ergodic measures come from? I know that there is an ergodic measure for each system, but maybe there are particular ones that I want to look at, and maybe there's a lot of them, and hopefully there are, because I want to do a limit with these things. So the variational principle. So variational principle. What it says is that the pressure. Well, I should tell you what pressure is first. Let's do pressure first. So, in order to like find these measures, I need to do something with the variational principle, which is a characterization of it's a thermodynamic formal statement about the dynamics of the system. So, so for building the potentials or building the measures. What we do is we first look at some thermodynamic formal stuff. So I need to define a pressure. So given a conformal graph-directed Markov system, B and a family of potentials, one can define the pressure with respect to T and Q is by definition equal to PT log phi prime, which is the Lyapunov family, plus QF, which is whatever family defines your F-exponent. And this is going to be equal to, by definition, the limit as n goes to infinity of 1 over n log of the sum omega with an EAN times this norm of the exponential of some sum with respect to that word of length n with regard to the family. And I don't really want to talk about what this S omega thing is again, because it can get, as you see, it probably looks gross already. But pressure can be hard to work with sometimes. And so all of my conformal graph-directed Markov systems in this talk are infinite alphabet. They in the paper they could be finite alphabet, and so there's like other cases that are considered in the paper. But this sum is always like an n or a naturals to the nth power sum, right? And so you're summing up it's a large discrete sum, and this norm, I should tell you what it is, right? This norm was a supremum norm, so where xt of omega is just a supremum norm restricted to the corresponding portion of the metric space. All right. Can do a barb so that it is there we go. Okay, yeah. so pressure can be not great to calculate, but there's some thermodynamic formalism that's already been developed that I don't have to work for in order to get information about pressure. And in order to make sure I can do things with pressure, I just need to make sure that it's finite and exists. And so one of the things that I prove is that we can go ahead and let D equal to the set of T and Q within the real plane such that this adjusted sum to the Q x T I to the T, this is a derivative. Yeah, there's a derivative here as well. It's just one derivative. It's not two. Okay. Just one derivative. There we go. That this guy is less than infinity. Take the set of all those points such that that sum is less than infinity. This is what we call the first partition-like function. So this guy is denoted as z1 tilde of T and Q in my paper, and this guy up here that's in this sum, this guy up here, this is the nth partition function. And one of the things that I show in the document is that if you have a point in here, so here's a lemma. So TQ is within D if and only if the pressure at TQ is finite. And the sketches that you go ahead and you for these Hölder functions, if your family is Hölder, right? So if our family is as at the beginning of the talk, then this if and only if hold. And the sketch of it is that if you have a Hölder family of functions, you sort of have this bounded distortion constant for that family, and you can bound the partition-like function above and below by this by the first partition function. And from some thermodynamic formalism theory, we know that when the first partition function is finite, so is the pressure, and that's an if and only if. So we show that. So the sketch is. Sketch, if I can write clearly, that would be great. The sketch is that you show that Z1 of TQ is less than infinity if and only if Z1 of TQ is less than infinity, which is if and only if the pressure is less than infinity. And this is a fact. This is a fact. And this is the content of proof. Comes in that first if and only if, which again just comes from doing some bounding above and below. So it's great. It's good to know when things are finite, and whenever things are finite, I can go ahead and make some measures by way of using some thermodynamic formalism and the variational principle. So now I can write down the variational principle. So the variational principle says that if you look at the pressure, and this is specialized to our situation, at some T and Q, this is going to be the supremum over measures that are ergodic for the system of the quantity of the topological entropy for that measure plus the integral over EA infinity of the corresponding amalgamated potential. And what's great about the variational principle is that if so the great thing about the variational principle is that for finitely irreducible conformal graph-directed Markov systems satisfying the strong open set condition, this supremum is achieved. And so we call this measure mu tq. In the document, it is mu tq tilde, but for us it will just be mu tq. And we call that an equilibrium state. So there exists mu tq and equilibrium state. That is, it is the measure that achieves this supremum above. Also, from the variational principle is that if we know that we have a equilibrium state and we remain in D, like we make sure that D is an open set, and there are some conditions for which you can guarantee that this D will be an open set. You can go ahead and take derivatives around every point. And the variational principle also lets us say that the derivative of pressure with respect to Q, and this is where we're forming this quantity that we can do numerics on, this will be equal to the integral over the symbol space of my amalgamated function of f with respect to the equilibrium state at TQ. And by Birkhoff's ergodic theorem, right? Again, this is just it's just a time average, right? This is just an F-exponent. This is for mu TQ almost every omega with an EA infinity, right? So I found a family of measures that detect exactly one F-exponent. Okay, so and that's the goal. So I want to tell you what we do with these, and so I'm almost done. This was around a 50-minute talk. We're about at minute 48, so I've just got some results to state, and then we will go ahead and finish off an example. So that will make all of this theory reduce down to a problem in calculus, which is kind of cool that you can do all of this work and then you get something that's just a calculus statement that you can easily calculate. So variational principle, what variational principle does for us is that it gives us our family of measures that detect one exponent. Now I want to be able to perform a limit on these measures. And so the way that we do this is, so this is some results from my paper. So what happens is, so I guess, so ND1, so ND, do I want to do ND1 right now? Right, so the question is, do these measures work? So I should say the conditions first. So one, so we need one, a comparability. Between F and the Lyapunov family. So for some alpha greater than 0, beta and gamma within the reals, minus alpha log phi I prime plus gamma is less than or equal to fi less than or equal to minus alpha log of vi prime plus beta. And here the question that people always ask is that if you have this comparability, does this trivialize the problem? Does this, and in particular, when you do the multifractal analysis, would this just trivialize the multifractal analysis where you're actually just looking at the same decomposition every single time? And the answer to that is no. This is shown in the Fon et al. Paper that is referenced in my paper, or that's the what my paper is generalization of. They show that the Kitchen decomposition and the Lyapunov decomposition are not isomorphic to each other. So this comparability condition is not as strong as it looks. And two, we need info about the second derivative of pressure. So again, these are not the results of my document yet. I'm just telling you what the assumptions are before I go ahead and give you those results. So in order to get information about the second derivative of pressure, luckily for Phi, finitely irreducible, and F Hölder, being in the Manhattan region, Phi being a finitely irreducible conformal graph-directed Markov system that satisfies the strong open set condition, and F being a Hölder family of potentials, and whenever you have TQ within your Manhattan region, this amalgamated function is not cohomologous to a constant, and this will imply that PTQ is strictly convex on D, which means that the second derivative of pressure is greater than 0 always, which is great because that tells me that this quantity is increasing in Q. So the conjecture, right, is which is actually a fact, right, is that we should limit Q to minus infinity of dp dq to get the minimum achievable F-exponent. And that's what my results that follow show. So first, right, so ND1, right, so if we fix some 0 less than equal to t less than or equal to the Hausdorff dimension of the limit set, and let Q within minus infinity to Q1 subset of minus infinity to minus 1 such that 0 Q1 is within D, then the families of measures or of equilibrium states where Q is less than Q1 and 0 is less than or equal to T is less than or equal to H, right? So for every T, there's a family. These are going to be tight, so are tight. And so Prohorov's theorem tell us that tight families of measures are relatively compact I spelled that wrong, but that's okay. And that's important because that gives us that whenever you have a decreasing sequence, so for every if there's a decreasing sequence, then there exists mu infinity equal to the limit as Q goes to minus infinity of mu TQ. All right, so we have this weak star limit of these measures, and the question is, okay, well, if I take a family, I do this limit for some decreasing sequence of Q's that goes to minus infinity, does that actually minimize the F exponent? And that's my second result, is that yes, in fact, that will minimize your F-exponent. And this is where we use comparability. So given comparability, as stated earlier, for any 0 less than or equal to t less than or equal to the Hausdorff dimension of the limit set, fixed, and qn to minus infinity, strictly decreasing, mu infinity is what we call f minimizing, or rather f tilde minimizing. That is the integral over EA infinity of f tilde d mu infinity is equal to c min. And that's great because I've solved this ergodic optimization problem of where are my extremal exponents, and it's not super. It's kind of a small point, but it requires a lot of details. Right? It's a small point in my multifractal analysis because this just gives me endpoints of my domain of my spectrum functions, but it required quite a bit of detail to get there. So I want to return to this example on Lou-Roth expansions. So in our example, and this will wrap up the talk. So in our example, we had a characteristic exponent of 2 log 2, but that is probably not minimal. So in this example, the pressure, right, for this family, let me do it in, I guess, this color. Yeah, let's do that. So the pressure is going to be equal to the limit as n goes to infinity of 1 over n log some. Oh, did I put my logs places? This is the one thing that people screw up when we do pressure. I know, I just got to the punchline and I'm taking a diversion. Yeah, I did logs. Okay, cool. I didn't screw it up 20 minutes ago. But so the pressure in this example is going to be 1 over n log some omega with an EAN of the product j is equal to 1 to the absolute value of sorry, not the absolute value, but the length of the word omega. So this is just n in disguise. Of 2 to the omega 1 times q minus t. And because all of these index sets are just the naturals to the nth power, and these things don't really, they only depend on the first coordinate, we get limit as n goes to infinity of 1 over n log of 2 to the q minus t over 1 minus 2 to the q minus t. Which is equal to, so like the n's will come out and cancel. So we can actually evaluate this limit. And that means that the derivative is also calculable in this case. So we'll get 2 log 2 over 2 to the t minus 2 to the q. And the limit as q goes to minus infinity is just log 2. So this is the extremal in the sense that it's minimal F-exponent, which in this case F was the Lyapunov family. So. And there's a question about is it achieved or not. Usually the minimal exponents are achieved on periodic points. But there's some, you could agonize about that a little bit, but it's not super important because the domains of my spectrum functions don't actually include the extremal exponents. They stop. They're open intervals that stop and begin at the extremal exponents. But yeah, so that does it. About an hour on the dot almost. So I'm going to go ahead and cut it there. Uh, Thank you for watching this documentation, or how much of it that you went through, of a talk that I gave about uh, this paper I wrote. Again, there it is. Okay. It's based on the first. So it's not the first section, but it's the first. It's sections 2 and 3 of this preprint that I've posted. That is actually, it should be submitted for peer review at this point as well too. So it has been submitted to a journal for peer review as well. So, but yeah. Anyway, that's it. Was definitely a more technical video, and it's just a documentation of a talk, so that's standard. But hopefully that gave you a little bit of a flavor of what I do, or have been doing in my dissertation research. Anyhow, alrighty, I'll see you later.